or Unit 5 of our financial modeling course. In this session, we are going to consider the time series models, that is the AR model, the MA models, and the ARIMA models, or autoregressive integrated moving average models. By the end of this session, you should be able to use various tests to determine the lag length need for a model in time series, and you should be able to specify the autoregressive model, the MA models, and the ARIMA models. Time series. In our earlier sessions, we have discussed the issue of time series, and now we are considering what constitutes a time series model. The time series data is one of the most common data sets that is being used in analysis for both finance and economics. Data generated sequentially in time are recorded and used also in engineering, environment, medicine, earth science, among other disciplines. Because of that, there are equally many time series models in the literature. The timestamps of this type of data present interesting properties that the models have to deal with in order to make meaningful decisions. Since data is recorded by time interval, they tend to be related in that sense. So we are saying that with time series, because the data is collected or gathered over time, then this is the real properties of the time series, which is time always play a key factor in the data that is being collected. It is assumed that the closer observations might have a strong dependency. So the frequency, that is how close the observations are, or like the frequency with which the data is being collected, also have some form of influence on the dependency between these time series analysis or the time series data. Such a situation is referred to as autoregressive because it deals with the value of the same variable. The econometric process of dealing with such dependency is what we know as autoregression. So by autoregression, we are simply looking at how the present values or the value of an asset is dependent on its lag values, that is its previous values. So in the next slide, we are going to consider autoregressive models. Autoregressive models. These models look exactly like a linear regression, but with the only difference being that they are simply regress on their lag values, or the lag values the of the of the return series or the asset price themselves. But autoregressive or AR model, we use autoregressive models to predict future behavior based on past behavior. As it is mostly used in forecasting when we assume that there is a correlation between values in a time series and the value that precede and succeed that value or that asset. The AR model operates under the premise that post values have an effect on current values, which makes the statistical techniques popular for analysis in both economics and finance and other disciplines. The auto regression indicate that it is a regression of the variable against its own self, so that is its own past values. Formally, the autoregressive model is specified as we can see here. So here we are looking at, we are saying that, let's say a value of an asset, let's say y, or let's say an asset y is dependent on a constant, a value that we mostly don't know, or the value of yt, given that we do not know the value of its previous values, and these are the parameters b1, b2, and up to bp. But the yt minus 1 is simply the lag value. So this is the immediate previous value of the y, that is the asset price, and this is the price or the value before this immediate present value up to the first value that was recorded or that was gathered, and this is the error term. So we are assuming that in an autoregressive model, our error term or the random term should possess this property, which is it should be identically and independent and identically distributed with an average of 0, and it should possess possess a variance. This is the autoregressive model with a p lag values, or that is an infinite lag values. And mostly autoregressive model is mostly at the heart of time series analysis. It is something that you have to understand or you have to know. And the estimated model above is known as the autoregressive for a lag p, that is for an infinite lag values. Another approach in modeling time series is to use past forecast errors in a regression like model. So that is what we call the moving average. We specify this as a moving average model which lagged K lagged errors. MA, or simply the moving average model, is a simple technical analysis tool that smooths out price data by creating a constantly updated average prices. The average is then taken over a specified period of time, like let's say it could be in days like 10 days, 20 days, it could be in minutes, like 20-30 minutes, or it could be in weeks, that is 30 weeks, 20 weeks, or 50 weeks, or any other time period that the investor chooses. Moving average strategies are also popular and can be tailored to any time frame, suiting both the long-term and the short-term investors. The most common application of moving averages are to identify trend direction and also to determine support and resistance level. So we use the moving average in depicting or in estimating or predicting the trend and also the resistance level of a particular asset. When asset price cross over the moving average, it may operate a trading signal for technical traders. We have a simple moving averages could be categorized as either simple moving average or exponential moving average. The equation that we have here is simply an equation of a moving average. So this shows a moving average where we have a constant and error term. So here with the moving average, our focus is not on the averages, but is on the error term. So you could see that we have the lags of the error term. Here we are focusing on the lags of the error term. So this is what we call the moving average model. But we can also estimate the moving average model from the autoregressive model. So the AR model can be rewritten as a moving average through repeated substitution. So an example of this series could be observed below. So here we have a YT, which is an AR model, equal to BYT beta 1 YT minus 1 plus error time. So here we are estimating our autoregressive model using a moving average model. And we're saying that in estimating the autoregressive using a moving average model, it should be equal to infinity, because we have an infinite number of moving average which is making up the autoregressive model. And we can see a pattern emerging from this equation or this model, given that the beta coefficient is less than 1, which is necessary for mean reversion. The value of the beta up to its kth number gets smaller and smaller as we move on estimating this autoregressive model. Therefore, the equation above becomes yt equal to the error term plus the shift parameter, or the shift coefficient, plus multiplied by the error term up to its finite value, or the last value. Similarly, the MA process can also be rewritten as such. Autoregressive integrated moving averages. So if you hear the term autoregressive integrated moving average, what comes into mind is that you've come across autoregressive model and also moving average model. So the only difference is the integrated. So it's like combining these three. So in statistics and in econometrics and in time series analysis, an ARIMA model, or what we call the autoregressive integrated moving average model, is simply a generalization of an autoregressive moving average which is a combination of both the autoregressive model and the moving average model. An ARIMA model is a statistical analysis that uses time series data to either better understand the data set or predict future trend. A statistical model, that is the autoregressive model we used earlier, or we've discussed earlier, is used in predicting the future values using the past values or the lag values. An ARIMA model is a form of regression analysis that gauges the strength of one dependent variable relative to other variable which is changing, or other changing variable. The model's goal is to predict future securities or financial market movement by simply examining the differences between the values in the series instead of true actual values. The ARIMA models can simply be understood by outlining each of its components. The ARIMA models combines the autoregressive properties, the integrated properties, and the moving average properties. By the AI, or the autoregressive properties, or the components of the ARIMA model, we are saying that this refers to a model the AI model refers to a model that shows a changing variable that regresses on its own lagged or prior values. The integrated is simply saying that the differencing of the raw observation allows the time series analysis to process the stationary data. So the integrated portion or components of the ARIMA model is simply looking at the stationarity of the series, and the moving average is simply incorporate the dependency between an observation and a residual error from a moving average model applied to its own lag observation. So to achieve in statistics, the preference is for us to achieve parsimony. That is, our model should be simple. In short, it should be simple. So to achieve these simple models or parsimonious models, we merge the autoregressive model and the moving average model to attain the ARIMA model. Here, our P is the number of lags of the autoregressive model, and the D is the number of times of differencing required to make the series stationary, as we say, which is the integrated portion of the model, and the Q refers to the number of lagged errors in the MA model. So we are looking at the P, which is the lags of the autoregressive model, and D, which is the stationarity series that we say, which covers the integrated portion of the term, that is the ARIMA model, and the Q is simply the lags of the moving average model. Some authors refer to the number of differencing as the order of integration denoted by ID. So the number of times that we difference our series in order to make it stationary is what we refer to as the integrated. So the integrated portion simply has to do with we difference in our data set in order to make it stationary. That's a series denoted by IO is stationary, and one denoted by II was difference once in order to make it stationary. So if a series is denoted like this, it simply means that it is already stationary. That is, the raw nature of the series is stationary. But if it is denoted in this form, that is I into bracket 1, it simply shows that we have to achieve stationarity by differencing the data once. So in summary, we have used the various tests to determine the lag length needs for a model in time series. We have been able to explain the concept of ARIMA models, which is made up of the autoregressive model, which we discussed earlier, and also the moving average model, which was also discussed. And we have also considered the issue of integrated series, or the integration in the ARIMA model, which we said is simply the idea of differencing the data set in order to make them stationary. We have come to the conclusion of this session. Thank you.